Hello everyone, this video is a discussion of a Laravel RESTful API project using PHP-FPM and Nginx with a Postgres database, all in Docker containers deployed in Kubernetes. So I'll cover the setup in Kubernetes, the choices and thought processes when configuring PHP-FPM and Nginx, the design of the development environment, testing, deployment, and some features of the API. Plus, there's a Vue.js frontend thrown in as well to log into the API and interact with it. It's a bit too simple to discuss in this video, but it's also included in the code. And all the code is in the repository in the video description. The production environment is my Kubernetes cluster at home with a single control plane and 2 worker nodes on a pretty slow internet connection. But that doesn't have too much impact on the project, and it can mostly be applied anywhere. The API itself has been kept generic, so you won't have to listen to any domain-specific concepts. The features I've added are focused on internal workings rather than a specific API use case, so they could be applied and expanded to many use cases. For example, responses are restricted to a set predictable structure, and each error has a unique integer error code, so the client can more easily handle error responses programmatically. Input validation for database columns with unique or foreign key constraints have been pushed to the database to reduce the number of queries needed. That's a controversial one, so we'll discuss the pros and the cons. There's also a fix for a very common Nginx inefficiency regarding HTTP compression. And there are some helpful logs to help us set the PHP, FPM, and Nginx configurations. So the structure of the video is production environment, PHP, FPM, and Nginx configuration, the Dockerfiles, the dev environment, and something of a CI/CD pipeline, but very minimal, and the Laravel API itself, and discussion of security considerations throughout. So what does the production cluster look like? The Ingress controller manages traffic for the cluster, handles TLS termination, and applies HTTP compression. It forwards API requests to the Nginx and Laravel pod. If traffic increases, the Nginx and Laravel pod is duplicated by a horizontal pod autoscaler. So as usual, we want to make sure that it's completely stateless. Then for the database, we're using Postgres, managed by a stateful set. Postgres 0 is the primary instance that all Laravel instances write to. Postgres 1 and 2 and so on are the read-only standby instances to increase read throughput if we have high concurrent usage. So whenever a new standby instance starts up, it duplicates the primary database with PG_base backup. And whenever the primary instance executes a write operation, it sends the WAL, or write ahead log, records to each standby, so that all instances are synchronized in near real time. To configure this in Laravel, in the database config file, add read and write elements to the database you're using, specifying the pod for the write instance and the service for the read instances. And for the development or testing environments, override that in the laravel.env file, specifying the database's service name in Docker Compose. For cache, we're using Redis. And of course, there's the Vue frontend, which is mostly decoupled. It could be hosted here or anywhere else. And finally, all these components are scraped by Prometheus, and Grafana molds that data into dashboards, which are also accessible through Ingress controller. Since the cluster has so few nodes, we can present the CPU and memory usage of each node in a single dashboard. And the other dashboard I watch most is for the Ingress controller, especially latencies for the three connected services, the API, the front end, and the Grafana front end we're using right now. On my slow home internet, the latencies don't help us model production systems very much. They're pretty slow. But the variance can still be insightful. The variance is expressed here with the average latency of the fastest 50%, 95%, and 99% of requests. In the Ingress controller, we're most commonly receiving requests from the CDN with the original client's IP in the X forwarded for header. So by specifying the CDN CIDR ranges that we trust, we can safely strip them from the forwarding chain and just leave the client's IP. That's important for logging and for rate limiting by IP address downstream in Nginx or Laravel. The Ingress controller, like any Nginx instance, generates a random request ID, and here we're attaching it to the web request with a custom header. And that way we can reference a consistent request ID here in the Ingress controller, and also as the request passes on through Nginx and Laravel and back again. Regarding HTTP compression, by default, gzip and brotli compress files of any size, but they both add metadata to the compressed files. So for files that are already small, we're actually expending CPU power to compress a file and actually increase the amount of data to be transferred. So we specify brotli min length and gzip min length to set the file size threshold at which the Ingress controller will apply compression. But what's the logical threshold to set? Well, the equilibrium point at which compression starts to reduce file size is different per file, but is usually between 100 and 400 kilobytes. So is that the answer? Well, not really. When we send a message over TCP, as long as the payload fits within one TCP segment, the size of that payload has a negligible impact on the transmission time. It's like adding more passengers to a plane. It has almost no impact on the flight time. So from the client's perspective, latency doesn't scale linearly with the file size. It potentially jumps stepwise when the file size necessitates sending another TCP segment. That means HTTP compression is worthwhile only if it has a decent likelihood of reducing the number of TCP segments needed to hold a particular payload. So a legitimate strategy is to set the HTTP compression threshold at the file size that would trigger a second TCP segment. The maximum size of a TCP segment depends on the MTU, the maximum transmission unit, on layer 3 of the OSI model, which is 1,500 bytes. Each IP packet has an IP header taking 20 to 60 bytes and a TCP header taking 20 to 40 bytes. And the rest of the 1,500 bytes is for the payload. For the largest possible payload that is still contained in one TCP segment, it would contain the TLS record for encryption, the HTTP headers, and finally, once all of that is accounted for, the remaining space is for the HTTP body, which is the candidate for compression. In this project, it's too early to finalize what our standard HTTP headers will be, so we can't finalize this optimization yet. But this is the formula that will decide it once all of the components are confirmed. But there's one last twist. If the response doesn't have a content length header, then Nginx ignores the gzip min length and brotli min length directives and compresses every file regardless of file size. So for that reason, in Laravel, we've got a middleware to measure the body and add the content length header. There's a php.ini directive called mbstring.func_overload. If we set it to 0, we can safely use the faster strlen function for adding the content length header. Otherwise, we'd need to use the multi-byte equivalent mb_strlen and specify 8-bit encoding to be sure we're getting the number of bytes instead of the character count. We have to make sure this middleware is late in the stack after any middleware that will modify the body, because if the response body is longer than the content length header, Nginx will cut off the excess. Okay, onto Laravel and Nginx. There are 4 ways of connecting PHP-FPM with Nginx in Kubernetes. The first decision is whether to put the containers in separate pods or in the same pod. Nginx can handle far more connections than PHP-FPM can, and separate pods would let us scale them independently, so we could save the memory overhead of the excess Nginx pods. Each Nginx pod has an overhead of about 10 megabytes. The downside is that Nginx could forward requests to PHP-FPM instances on different nodes, which would add network latency. Getting around this is fiddly and might not be worth the memory saved. Also, separate pods means that the logs for a particular request would be split up between different pods. If we go with a single pod, that opens up the choice of how Nginx and PHP-FPM will talk to each other, either by using TCP or by mounting a shared volume onto both containers to hold a Unix socket file. Each TCP connection needs to be established with a TCP handshake consisting of 3 messages sent back and forth. With the default Nginx configuration, that handshake happens for every single request routed to PHP-FPM. Each message sent is bundled with IP and TCP headers, increasing the amount of data to be transferred. And depending on the size of the request and the response, they might be broken up into packets before sending, then reassembled at the other end. And finally, the connection needs to be torn down with another 3 messages. Due to all this redundant stuff, I really expected sockets to be measurably faster than TCP. Maybe the teardown would happen concurrently to the response being sent out, but the rest of it surely increases latency. However, in the very quick tests that I set up, latency was almost identical between the 2 methods. That's interesting academically, and I want to investigate more when I have the time. But practically speaking, if we're interested in such small savings in latency, then we'd likely be better off considering SWL instead of PHP-FPM and Nginx. And then this whole architectural decision would go away. Both TCP and sockets benefit from the Nginx directive fastcgi keep con, which keeps the connection open between requests, so we wouldn't need the TCP handshake for every request. The PHP-FPM counterparts are pm.processIdleTimeout, which sets the time a worker can be idle before it's killed, and pm.maxRequests, which caps how many requests a worker can serve before it's respawned. And we need to set fastcgi pass in Nginx and listen in PHP-FPM. For TCP connections, we tell them which port, and for socket, we tell them the location of the socket file. Then the fourth and final option for connecting Nginx with PHP-FPM in Kubernetes is putting them in the same container in the same pod. This is workable, but it creates complications. Kubernetes monitors the status of the process with PID1 as a health check. If the process exits, Kubernetes stops the container, even if other processes are running. And if another process exits, Kubernetes has no idea and does nothing. So if a container has more than one key process, we need to implement a replacement for the Kubernetes health checks and process management. In the end, I went with the middle ground option of same pod, different containers, with shared volume between them for a Unix socket file, mostly because I hadn't tried this setup before. And we'll see the detailed implementation in the Kubernetes manifest and the Dockerfile later in the video. So with that decided, let's jump into the pod manifest. As I explain components, I'll also build up this visual representation to help visualize how everything links together. Obviously, the Laravel and Nginx containers are at the core, and the first step is to inject the configuration files with Kubernetes secrets and config maps, and to mount the shared volume for PHP-FPM to create the socket file we just talked about. If we can make the whole file system in a container read-only, that's great for security. So we need to identify where the application needs write access, and then mount volumes at those locations with write access, and make everything else read-only. And the socket volume is our first one of those. The Laravel bootstrap caches never change in production. So at first thought, we'd run the cache creation commands in the Dockerfile so that they're part of the image, and then we'd make them read-only in production. That's fine for event cache, root cache, and view cache, but config cache needs to read the .env file. For security reasons, we can't put sensitive files like the .env into the image. So the only safe option is to run config cache within each pod as it starts up. So that means the cache directory needs to have write access in production, but we'd prefer it to only have read access because it never changes once created. And any attacker that gets write access to the bootstrap caches could obviously do serious damage. But there is a way to get the best of both worlds. First, in the Dockerfile, we rename the bootstrap/cache directory to something else, like cache temp. Then, in Kubernetes, we run a Laravel init container when the pod starts up. It has the .env file injected and a writable volume mounted at bootstrap/cache. We copy everything from the temp cache directory into the volume at bootstrap/cache, and then run php-artisan config cache to create the final bootstrap cache file. The time command just logs the memory usage to help us set resource limits later. Then, after the init container has finished, the main Laravel container starts up with the cache volume mounted as read-only true. And that's how we get read-only cache with sensitive data compiled at the pod startup. We're also running additive database migrations in the init container. The -- isolated flag is very consequential. It means while this migration is running, although normal reads and writes can still happen concurrently, no other migrate command with the isolated flag can begin. A migrate command without the isolated flag can still run, so it's important that we add it to every migrate command in production to make sure concurrent migrations are impossible. It uses the cache to track whether the isolated command is running or not currently. So if you're using the database for cache, it creates a catch-22 situation for your first migration. You'd need to run migrations once without the isolated flag first. But most applications would just use Redis, so it wouldn't be a problem. An unexpected problem I ran into is that if a container crashes and gets restarted by Kubernetes, the mounted volumes are not cleared. That's the behavior we want most of the time. We want data to be permanent for the life of the pod. But it can cause some misleading error logs. In the init container startup script, it copied and created the cache files with no problem. Then it hit an error with migrations. So Kubernetes killed the container and ran it again. But on the second run, the volume was already populated, so the error logs were about file permissions, not the migration commands. So just bear that in mind. If all else is equal, move any operations on mounted volumes to the end of the script. But in our case, migrations actually depend on the cache files being present. We've got another init container to set up the directory structure for Nginx's writable volume. I prefer to use chain guard images to be minimal and more secure, but the CPUs of my nodes are too old and don't support them. And finally, we have one last container that scrapes the Nginx metrics endpoint and presents that data in a format that Prometheus can then scrape. Port 8080 is for publicly available endpoints via Ingress. Port 8081 is for internal traffic like health checks and metrics. And then Prometheus scrapes the exporter on its default port 9113. Kubernetes provides three types of probes or health checks. Probes are attached to containers, but the actions on success or failure can impact either that container it's attached to or the whole pod. When a pod starts up, if at least one container has a startup probe, then that pod won't initially be added to the service's endpoints, so it won't be accessible by other pods or by outside traffic from Ingress. If a startup probe fails, the container it's attached to is killed, and by default configuration in Kubernetes, any killed container is instantly restarted. So that's hoping that a restart or a slight delay will fix whatever caused the startup probe to fail. Once a container's startup probe passes, it will never run again, and instead the container's readiness probe and liveness probe begin running if it has them. And they will then run repeatedly for as long as the pod exists. Once all startup probes in a pod pass, and if there are no readiness probes, then the pod is added to the service's endpoints and it starts serving traffic. If there are one or more readiness probes, then the pod waits on them. Once all readiness probes pass, the pod is added to the service's endpoints. But the readiness probes keep running continuously, and if at any time a readiness probe fails, the pod is removed again. So a failed readiness probe only has a pod level effect. It doesn't kill the container. That's what liveness probes are for. When a liveness probe fails, it has no pod level effect. The pod can still receive external traffic. Instead, a failed liveness probe kills the container it's attached to. So to summarize, a failed readiness probe stops traffic flow reaching the pod. A failed liveness probe kills the container it's attached to. And a failed startup probe does both of those, but only when the pod is starting up. Phew, I think that's the most concise summary of probes I can give. So how can we apply these to our Laravel and Nginx pod? Well, we don't want requests reaching a broken pod, so a readiness check is crucial. And the ability to serve requests depends on Nginx and Laravel both working. So we put the readiness probe on the Nginx container to query a Laravel endpoint that returns a simple plain text response. That means the readiness check only passes if Nginx and Laravel and their connection are all fine. The ability to serve requests also depends on the connection to the database and the cache. So we might consider checking those connections as part of the readiness check. But if a database problem did occur, it would affect all Laravel pods. We wouldn't have a mix of healthy and unhealthy pods. And the readiness probe would react by removing this pod from its service, which doesn't do anything to solve the database problem, and actually we'd slightly prefer to keep the Laravel pod serving requests to give as graceful a response as possible. And then we'd rely on some other probe to heal the database problem closer to where it occurred. So no, the readiness probe should not check the connections to the database and cache. However, it is a good idea to add those connections to the startup probe. That's so that if we're deploying a new version and I've messed up the connection configurations, Kubernetes will stop it going live and keeps the old version alive, serving requests. Another reason to have a startup check is because we're doing opcache preloading at startup, so we need some flexibility around the slightly unpredictable boot up time. The startup probe, of course, also needs to check both Nginx and Laravel and their connection. So we add it to the Nginx container and call a startup endpoint in Laravel. This design has one perverse side effect that if the startup probe fails, it kills the Nginx container it's attached to, even though the problem is much more likely to come from the Laravel container or the database or cache connections. But that's one imperfection I think we can live with. And finally, what about liveness probes? Well, in the Nginx configuration, I created an endpoint that returns a simple plain text response. But I think the chance of Nginx messing up is so unlikely, currently I don't think it's worth running a constant probe. Laravel is a bit more likely to mess up, so we've got a liveness probe querying the PHP-FPM status page. The last big topic of this manifest is the memory limits that Kubernetes imposes on each container. So this is where we'll transition to the topic of configuration for PHP, PHP-FPM, and Nginx. The Kubernetes memory limit is a fail-safe that kills the container if it's exceeded. That's a pretty drastic action, so we need to set it high enough to cover the peak memory usage in normal operation, so that it's only triggered by abnormal memory usage that we want to catch early and contain. This is my formula to estimate peak usage in normal operation. My understanding can be improved further, but I think this is a decent formula for now. And at the end, we use a margin component to represent the degree of confidence we have in our estimation. PHP-FPM has one master process and a variable number of workers that serve web requests. So we need to determine which memory expenses are per worker and which are shared between all workers. The master process overhead, the PHP interpreter and its extensions, opcache, and any mounted volumes stored in memory should all be counted once. And then everything in the brackets is multiplied by the maximum number of workers specified by the PHP-FPM directive, pm.maxchildren. For an application that's 100% CPU intensive, we'd set pm.maxchildren equal to the number of CPU cores available to the container. But the larger the I/O weight is expected to be, like waiting for database queries to come back, the more we can raise pm.maxchildren above the number of cores. Workers process one request at a time, so memory usage doesn't scale infinitely as the concurrency of requests grow. The number of workers is a cutoff, so pm.maxchildren is the ultimate cutoff. And any queue of waiting requests mostly consumes Nginx's memory allowance, not PHP-FPM's. Memory_limit in php.ini is the memory usage failsafe on script execution. So just like the Kubernetes memory limit, we need to predict the peak memory usage in normal operation of a single script this time and add a margin of confidence. If abnormal memory usage happens in a script, we want the PHP memory limit to kill that script. And the additional margin of the Kubernetes memory limit means it can only be triggered in an even rarer and more extreme situation, and it would kill the whole container, not just a single request. To help set PHP's memory limit, in Laravel we're logging the peak memory usage for every request. Similarly, we're also logging the real path cache size and the worker ID. Doing it in the middleware's terminate method means it's executed after the response is sent out. We can also use xdebug profiling to find exactly how memory is used in a particular request execution. And while profiling, in Laravel we should disable garbage collection at the start of the script to ensure accurate readings. So there's a setting in the .env file to toggle garbage collection. We have a similar structure for the Nginx prediction of peak memory usage in normal operation. Shared resources are counted once, and the items in brackets are per connection, so they get multiplied by worker processes, which is the number of workers, and worker connections, which is the maximum number of connections per worker. The default for worker connections is 512, and that can realistically be set as high as 10,000 or more. That means that since we will add a margin of confidence to each of these buffer sizes here to ensure they can satisfy legitimate requests, those margins would then be multiplied thousands or tens of thousands of times when we're calculating the container level memory limit. We would then be reserving a huge amount of memory for a peak usage scenario that is very unlikely to occur. So to manage that problem, first, we need to align worker connections with the peak request concurrency we want to guarantee satisfying, and with the memory or the financial constraints that we have. Second, let's consider the size of these buffers extremely carefully. Can we restrict them without hurting UX? Does exceeding a particular buffer kill a request, or does it just downgrade performance, and by how much? So with that as our goal, how do these buffers work? For an incoming request, Nginx puts the headers into the client header buffer. If the headers exceed that buffer, Nginx puts them into the large client header buffers. And if in that scenario the initial client header buffer is no longer used, we could safely remove that from our peak usage formula. But I haven't had time to experiment with that yet, so I'm keeping it in just to be safe. If the large client header buffers are exceeded, Nginx returns a 400 bad request error. That's a pretty drastic action, so we can't squeeze this buffer too tightly, especially if we have a broad or a non-technical user base. But if our API end users are technical enough, we could put a low but reasonable limit on the size of the request headers, and then require users to read and abide by the documentation. Nginx stores the request body in the client body buffer, and any excess is stored on disk, so we can be more aggressive with this buffer, maybe only guaranteeing it will hold the bodies of 95% or 99% of legitimate requests. For an Nginx instance that only serves static assets, like the Nginx serving our Vue.js frontend, legitimate users will never send post, put, or patch requests. So we can set the client body buffer size very low, but we'd still need to count it in our formula because users can still fill up that buffer. So we don't want to give malicious users the ability to trigger our memory limit and kill the Nginx container. After receiving the request line and the headers, Nginx compiles them to determine how to route the request. Some of the requests will be sent to PHP-FPM, and it will run the Laravel application to build the response, which will then be sent back to Nginx. The first part of the output from PHP-FPM is stored in the preliminary buffer determined by fastCGI buffer size. It's crucial that the fastCGI headers are fully included in this preliminary buffer, because if not, Nginx returns a 502 bad gateway error. These fastCGI headers are what will later be translated into the response's HTTP status and HTTP headers. So we need to be very aware of and control the size of the headers returned by Laravel. In the Nginx access log, we're recording the embedded variables upstream response length, which is the total size of the response payload sent from PHP-FPM, and body bytes sent, which is the size of the response body. So the total minus the body gives us the size of the headers. This is likely to be much smaller than the size of the equivalent HTTP headers because it's in binary key value format and doesn't include endline characters. Any headers added by Nginx are not held in this buffer because they're added as the response is sent out. If this preliminary CGI buffer fully contains the headers, the rest of the buffer is put to good use and fills up with the first part of the response body. So there's no memory saving benefit to squeezing this buffer aggressively. If the response exceeds the preliminary buffer, the rest of the body is stored in fastCGI buffers. Yes, that's named confusingly. What I'm calling the preliminary buffer is determined by the Nginx directive fastCGI buffer size. And then these body-only buffers are determined by fastCGI buffers. If these body-only buffers are also exceeded, Nginx responds with a 502 bad gateway. So we need to be very aware of the maximum size of our responses. The value of upstream response length in our logs will help with that. If we can control the response size with a high degree of confidence, we can set these buffers quite tightly. And then we'd need to set up a system such that any design or code-based change that affects the maximum response size triggers a reassessment of this configuration before deployment. And we'd also need to implement end-to-end tests for the scenarios that generate the largest possible responses in production. It's possible that Nginx clears the request buffers before the response buffers are filled. If that's the case, we could safely use the max of the request buffers and the response buffers instead of the sum, and that would then reduce our peak memory estimate by quite a lot. That would be very interesting to examine, but I haven't had the time to do that yet. For an Nginx instance that only serves static assets, it's impossible for a request to use the fastCGI buffers, not to mention the proxy or the output buffers not mentioned here. So we can safely remove those from our peak usage formula for that instance. And the Ingress controller handles TLS termination, so we're also ignoring SSL buffer here. PHP, PHP-FPM, and Nginx all have settings for timeouts that govern various parts of the request-response process. So I created this diagram for my notes to help visualize how they line up. The x-axis represents time, very roughly, as the request goes from client to Nginx to PHP-FPM, and the response reverses that route. But the size of each block doesn't correspond to how long the task takes or the suggested timeout value. Rather, the diagram shows how and when each timeout is triggered and how they overlap. If any of these timeouts are breached, the client receives an error response. So we want these timeouts to accommodate essentially 100% of legitimate requests. Starting from the left, the first timeout is client header timeout, which is triggered when Nginx accepts the connection after the TCP handshake. It sets the time needed to receive the request line and the headers from the client. It's not an absolute timeout, rather it's a timeout for the intervals between reads. That is, each time some part of the header is received, the timer resets to 0. And that's a running theme for a lot of these Nginx timeouts, as you can see in the diagram. After Nginx receives and parses the request line and the headers, the client body timeout begins and limits the intervals between reads of the request body from the client. The purpose of these two request timeouts is to stop partial requests filling up the available connections. A slow loris attack is an attempt to do that en masse, and a clever attacker could easily determine our timeouts and then drip feed the server with a response repeatedly. So it's important to also limit concurrent requests from the same IP address. So we store all concurrent IP addresses with limit con zone. With my settings, there can be a maximum of 2048 concurrent connections. So that needs 124 kilobytes to guarantee storing all concurrent addresses. Then, in a server or location block, use limit con to put an upper limit on the number of concurrent connections from the same IP address. Back to timeouts. After the header has been received, Nginx can determine how to process the request. If it will be forwarded to PHP-FPM, and if the Nginx worker doesn't already have a connection with an idle PHP-FPM worker, it starts a new connection and starts the fastCGI connect timeout. In normal operation, establishing a connection is near instantaneous, unless all PHP-FPM workers are busy and the queue is filled up. The queue size is determined by the PHP-FPM directive listen.backlog, so it's advisable to set it to the maximum 511, and then set fastCGI connect timeout to just a few seconds. Once the body is fully received and the fastCGI connection is established, Nginx begins sending the request to PHP-FPM and starts the fastCGI send timeout, and PHP starts the max input time. Max input time also covers the parsing of the request body, like populating the $_post or $_files predefined variables, before the script can begin execution. But of course, Nginx doesn't know about or care about any of that. So as soon as the transmission is complete, it switches from the fastCGI send timeout to the fastCGI read timeout, which puts a limit on how long Laravel can take to return the response in full. More accurately, it puts a limit on the interval between read operations. But since Laravel typically buffers the whole response and sends it out at the end, that makes fastCGI read timeout almost the same as an absolute timeout. The execution time of the PHP script is limited by PHP's max execution time and by PHP-FPM's request terminate timeout. Max execution time measures CPU time, so the timer is paused during I/O operations like database queries, and when exceeded it has a slightly more graceful termination, whereas request terminate timeout measures wall clock time and it has a hard termination. So we'd align these two, but then we'd increase request terminate timeout to account for the peak expected I/O time. And then we'd also add a little margin to give max execution time a chance to terminate the script more gracefully. After returning the response in full, if the PHP script continues execution, as in with the terminate method in middleware, this is included in max execution time and request terminate timeout, but not in Nginx's fast CGI read timeout, because once Nginx has received the response, it's already moved on to sending it to the client. So the script execution timeouts can extend rightwards beyond T5 in the diagram, and maybe beyond the end of Nginx's fast CGI read timeout, though in that situation it's probably better to use queue workers instead. To help set the script execution timeouts, in Laravel we're logging wall clock duration and CPU time duration for each request. And finally, at the right of the diagram, send timeout limits the intervals between write operations while sending the response to the client. Nginx has 4 embedded variables which we can log to help us with setting some of these timeouts. Request time measures from the first byte received from the client to the last byte sent to the client. Upstream connect time measures the time to establish the fast CGI connection. That should hopefully always be 0. Upstream header time measures from the first byte sent to PHP-FPM until the first byte received in response by Nginx. And upstream response time has the same start point, but keeps measuring until the last byte of the response is received by Nginx. Those two will be the same unless the response is very large. In the Laravel documentation, the suggested Nginx configuration is really not great. As an example, let's say a user sends a request to our domain /hello. So this embedded variable $URI equals hello. With this configuration, what we're asking Nginx to do is this. First, check for a file called hello, and if it exists, serve that file to the client. So far so good. That could be a JS file or a CSS file. But if hello file doesn't exist, check for a directory called hello. If hello directory exists, check for an index file, which above is defined as index.php. If that exists, serve it to the client. And already, from a Laravel perspective, we are way off course. If hello directory didn't contain index.php, then serve the directory listing, which very ancient internet users will remember, but these days, directory listings are disabled by default. So Nginx returns 403 forbidden, simply because the user requested a directory which does exist on the server. And if the request URI isn't a file and isn't a directory, finally we're directed to the Laravel application index.php. But I don't understand why index.php here is so convoluted with variables. If not to a static file, we always want to forward to public/index.php. So why not just hardcode it here and state it clearly? And these headers at the moment are functional, but the moment we put an add header directive into a location block, that block no longer inherits add header directives from outside. So it's safer to just put all add header directives into location blocks and don't rely on inheritance. This whole configuration feels like a copy-paste job from a pre-Laravel PHP project, and although it works, it has needless inefficiencies and potential security flaws. For our Nginx configuration on port 8080, we want all responses to be JSON, including errors caught by Nginx. So for the error pages, we're using named locations that serve static JSON files saved into the image. Internal locations would also achieve the same result. Then, apart from the fav icon and robots.txt, we're returning 404 for any request that doesn't start with /API/v1/. And if we take a look at the standard hacky requests that every server gets, this location block alone rejects, well, all of them. We definitely don't want any malicious requests like this to access any static files, and preferably we don't want to waste resources forwarding the request to Laravel just for it to return a 404 response. All API requests get sent to Laravel, and index.php is hard-coded for clarity. Finally, we're rate limiting by IP address here in Nginx, and later by user ID in the Laravel application. Then for port 8081, for cluster internal traffic, we've got keep alive times to sustain TCP connections with Nginx exporter, and the readiness check for 1 week and for 2 weeks, respectively. /Nginx up is a simple Nginx only endpoint for a liveness check, which we're currently not using. /Nginx status is for the Nginx exporter to scrape Nginx metrics and in turn be scraped by Prometheus. And the rest are specific endpoints to send to Laravel. In the Vue.js Nginx instance, if a request URI ends in one of these file extensions, we check if the static file exists, and if not, return index.html, and the Vue.js router will send the 404 page. And then for non-static asset URIs, go straight to index.html. In the content security policy header, we need to specify the API domain for connect source and form action. For static assets, we can cache the results of the stat and open system calls. And since we're using immutable containers, we can safely cache for a year or more. And then the static assets themselves will likely be held in memory by Linux's page cache, though that depends on other containers in the same node. Let's take a quick look at the Dockerfiles. For the Laravel image, some dependencies are needed at build time for compiling PHP extensions and running Composer install, but not needed at runtime. So the overall design is compile in a builder target and then copy the results into a fresh minimal target for production. To accommodate other targets, which we'll discuss in a second, we have to split builder and build prod targets and split minimal base and prod targets, with prod being the ultimate image to deploy in production. During the build phase, the composer install command only needs composer.json and composer.lock, but creating the autoloader obviously needs the entire codebase. So a very efficient Docker caching strategy is to copy in the .json and .lock files, run composer install with the --no autoloader flag. Then that intensive process is cached until we change our composer dependencies. Then we can copy in the codebase and build the autoloader, If we didn't split those commands, we'd need to build the vendor directory every time we modify a file. In the production image, for PHP-FPM to communicate with the Nginx container, both processes need read and write access to the socket file. So we make sure that the www data user in this container and the Nginx user in the Nginx container have the same UID, and then set the file permissions accordingly in the PHP-FPM configuration. As mentioned in the Kubernetes section, we run all Bootstrap caches except for config cache in the Dockerfile. And we're not using Laravel's built-in health checker endpoint, but if we were, apparently that view isn't cached by PHP artisan view cache. So we can access it once in the Dockerfile to force that view to be rendered so that we can make the cache directory read-only in production. For file permissions, I've commented out some of my standard Laravel production setup because they don't apply in Kubernetes or for this particular project, but I like to keep them here just as a reminder or if we change the project or architecture later. For the local dev environment, the simplest option is to extend the builder target just before the composer install command is run. Then, install development tools like Xdebug and create a directory for the output from Xdebug profiling. And then mount the local codebase into the container in Docker Compose with a bind mount. We want to run composer install and artisan commands inside this container to write files to our local device. So in the Makefile, we can construct a command to enter the container with the www data user and our local user's group GID, and then set umask to make sure that any files generated have 775 permissions, as in full permissions for both user and group. That way, the vendor directory and any other files created by this container are readable and writable by the www data user in this container and our local user on the host. I've also got a combined target for testing the architectural option of PHP-FPM and Nginx in a single container, which we discussed earlier. The only complaint with this dev image is that it has different dependencies to the production image. So potentially some tests could be passing in this image, but be failing for production. This is a trade-off I'm happy with, but an alternative, more complex approach would be to run composer install with testing dependencies included. Then copy the resultant vendor directory into a target that splits from the production image just before the codebase is copied in, and then mount the local codebase with a bind mount. And similarly for the dev environment, split off from minimal base and install dev tools like Xdebug. The local development environment is handled by Docker Compose. There's not too much to note here. Nginx depends on the Laravel container, and service started is enough because we just need the socket file to exist before Nginx starts. Ideally, Laravel should depend on Postgres and Redis passing health checks. Postgres has a handy pg_isReady command, and Redis has ping. But I commented out the dependencies since very often I was just testing Nginx and PHP only and didn't want to wait an extra 2 seconds to get running. There are 2 instances of Postgres, one for the dev environment and one for testing. It's most common to run tests with an in-memory instance of SQLite as the database. But as we'll see later, our application is unfortunately tightly coupled to Postgres. So we need to run the tests with Postgres to have any confidence that the results represent the application in production. There's a pre-commit script to process the code before committing to Git repository. For Vue.js, lint staged handles things pretty well. we're running prettier, ESLint and vtest on only staged files that have changed since the last commit, and running view tsc on the whole project. In a similar way, in the bash script, we've got a function that returns an array of the staged files that have changed since the last commit, so that we're not wasting time and resources checking the whole codebase on each commit. For scripts, we feed that array into shell check linter. And for PHP, we're validating the composer.json and .log files, then feeding the changed files array into PHP-stan at level 9 and pint, and then running git add to restage any files that were modified. Each makes sure to reference the correct configuration file, and we have a stricter pint configuration for non-tests than for tests. And the last step is to run PHP unit. It executes a script mounted in the Laravel container which accepts arguments for whether or not to first run database migrations, the test coverage threshold, test suites to include or exclude, and which tests specifically to run. Since I'm not working as part of a team, a Makefile is sufficient for a CI/CD pipeline for testing, building, and deploying. exec Laravel executes a command in the Laravel container. Very often, we're creating or editing files on the host machine via a bind mount. So we enter the container with both the www data user and the local users group, so we can function in both worlds. And we're setting umask so that any files created have 775 permissions, so that both the containers user and the local user can read and write the files created. Shell Laravel executes an interactive shell in the container. The composer commands have the same function and are just time savers to do specific composer functions without opening an interactive terminal. And then there are similar exec and shell commands for each container. If we want to run PHP-stan, pint, or PHP-unit outside of the pre-commit check, those commands are here. For testing, there are commands for the standard test suite and for end-to-end tests for testing a deployment. Then there are commands for building the images and for deploying them in Kubernetes. We can switch contexts between the local kind cluster and my physical cluster. For this API, I want every response to fit within a small set of predictable JSON structures. The top level of the response should always be an object, not an array, to avoid JSON array hijacking. And for every response object, we attach an object called meta, which at least includes a request ID to help clients communicate problems with us and help with debugging. I'm also including the timestamp and script duration for now, but these don't have any practical purpose at the moment. For a query that returns a single resource, the resource is the value of a key called data. For a query that returns multiple resources, data is an array of results. And we add an object called pagination to help the client navigate through the dataset. For a successful query with no resource to return, data just contains result success. And finally, if at least one error occurs, data is replaced by an array called errors, which contains error objects which each have an integer code and a string message. These error codes help the client to respond programmatically to a problem without needing to parse the message text. The error itself is a data transfer object called API error, and the code is an integer enum called API error code. API error code has a method called message, which accepts an array of placeholders if necessary and returns an appropriate message for each error code. And the API error constructor calls this message method. So API error code is a very convenient single location to plan and construct a list of all possible errors, pair them up with a suitable message, and a reference point for the placeholders that we need to pass to the API error constructor. The aim is to be as specific as possible with error codes, but also to have more general error codes to fall back on. For example, we have specific error codes for each type of input validation employed in our project. But if something goes wrong, there's a general validation error code. So if we use a new type of input validation in a controller or form request, but we don't account for it in our validation error handler, we can still return a semi-specific error response. And in the worst case scenario, we can fall back on the unknown error code. Of course, when such general errors happen, we need to analyze the logs and construct more insightful error codes as a result. The JSON response structures mentioned each have a method in the class called API Response Builder. Success, paginated, errors. And as well as the errors method, there's also an error method, because returning a single error is the most common scenario, and it's easy to forget to enclose it in an array. Since we want to always send JSON responses with descriptive error codes, we want to replace Laravel's default exception handling behavior. In Laravel 11 onwards, that's done in bootstrap/app.php. But since it's likely to get quite sizable, I've extracted it to a class called API Exception Handler. In simple cases, we can just define an error response with API Response Builder. In some cases, there's a small amount of processing to add more detail to the error response. And there's a catch-all default for any exception we're not handling specifically. For input validation errors, I've extracted the logic to Validation Errors Builder, which returns an array of the data transfer object API error to be fed into API Response Builder's errors method. In Validation Errors Builder, we loop through the errors returned by the validator and match each with the correct API error code. As mentioned throughout this project, whenever there's a scenario that we don't expect to happen, like if we fail to match the validation error, we log the details and fall back on a more general API error code. For the database, I have maybe something of a controversial feature, which I'll have to explain carefully. When we need to write to the database, and one of the columns has a unique constraint or a foreign key constraint, the standard practice is to first validate the value with a select query, and if no results are returned, then continue with the insert or update operation. So that's one database query for the failure scenario and two queries for the success scenario. But with a lot of caveats, we can potentially skip the validation in Laravel, write the value directly to the database, and if a constraint is violated, handle the error returned by the database and inform the user of the input validation error. That means only one database query for both success and failure scenarios, which reduces the load on the database and speeds up responses from the client's perspective. It also removes the race condition between the select query for the validation and the eventual write to database. So now for the downsides. 1. It splits the validation logic in two, which is messy. I kept the constraints in the form request as comments, as reminders of what will be validated by the database. 2. It's not great for the developer experience. We just have to remember to not validate constraints in form requests and to employ our new strategy each time we want to insert or update. 3. The database treats the constraint violation as an error, not as a simple validation check, and it logs it as such. So we'd need a log filtration system in production. 4. The database returns the error as a string, which we have to parse. And that is a somewhat fragile process. We need to run rigorous tests with many edge cases every time we change database version. And 5, error responses vary per vendor, so we're tightly coupling our application with our initial choice of database vendor, in this case, Postgres. These are all very serious cons, and nothing else about this project is geared towards the high concurrency situation that would give value to the pros. So for a real project, I would almost certainly not implement this feature. But I wanted to explore it as an educational exercise. And it's a healthy exercise to predict the cons in advance, try it, and run head-on into any unexpected cons, and then get better at analysis of design choices in the future. So far with Postgres, with unique and foreign key constraints, I haven't hit any critical problems from parsing the error message. It returns a unique SQL state code that identifies which constraint was violated, and the offending column is bounded by characters that are invalid for a column name and preceded by a substantial fixed string. Postgres does actually allow illegal characters in the column name if it's bounded by double quotes, so we'd have to check for that. Another nuisance is that Laravel interpolates the actual values into the Postgres error message, and for security, we don't want potentially sensitive values feeding into our parsing logic, especially for a fragile process like this that has a lot of logging. So it works for Postgres, but if for some reason we change database vendor, we'd need to rewrite the parsing logic, and there's no guarantee that the error message provides the required detail and format for us to parse. Here's the comparable message from SQLite. The SQL state code is more generic than Postgres's, so we'd have to parse the text to discover even which constraint was violated. There's also a small possibility that a new version of Postgres will change the error message in a way that hurts this feature. I implemented this feature with a trait called handles DB errors. For any code that inserts or updates a database record, we wrap it in a closure and in the handle DB errors method, and the closure is executed inside a try-catch block looking for query exception. This wrapping design causes very minimal disruption, and there's a low development cost to enabling or disabling the error handling feature. The design is very reusable, just add the trait to any class that writes to database, and compared to a rigid method signature, the closure gives us complete flexibility around what variables to pass, what type to return, which interface to use to interact with the database, how many queries to run, what parts of the code to wrap in a database transaction, and what other actions we need to run alongside the queries. Currently, if a constraint violation is detected, we're immediately returning a validation error response to the client. We could consider making this more flexible, like allowing more closures to be passed to handle specific error scenarios. For example, we might want to alter our reaction based on which column violated the constraint. Also regarding the database, we're implementing a rule of no select star queries, or no queries that return all columns. This is to reduce the chance of exposing sensitive data and to make queries faster to run. So for any resource that will be output by the API, we're defining a resource class, where we define how the raw output is processed into the API output. In this case, we're just renaming UUID into ID. And we're defining the columns to be injected into the select query to fetch only the relevant columns. For the naming scheme, we have the model name, item, then public or private, explicitly warning if this resource will be output by the API or not. For example, the UUID is for public usage, while the incrementing integer ID is strictly for internal usage. And we have full or minimal to denote which columns to include. Paginated results would typically use minimal, while the results of a single specified resource would typically use full and include more columns. Then, in the model class, it imports the columns constant to run the relevant queries. Let's run through the lifecycle of a standard request. The first thing we do is create an instance of request context service, which will hold auxiliary information about the request. We define it as a singleton so that any time it's referenced in a method signature throughout the application, the service container will inject the same instance with the same properties, similar to how request itself is handled. Immediately, we store the current time so that we can calculate the wall clock duration at the end of the script execution. And we store the current resource usage of the PHP-FPM worker process in order to calculate the CPU time duration at the end of the script. There's an empty array to store the duration of any database queries, which will also be logged at the end. And the request ID set way back in the Ingress controller is saved here and added to the context of any logs that will be written. The logging middleware will call getDuration milliseconds, which is pretty simple, and also getCPU time milliseconds, which requires some explanation. RUUTime.tvSec is the number of whole seconds the PHP-FPM worker process has spent in user mode, like the PHP interpreter doing work. The same key with USEC, or microseconds, instead of sec, is the number of microseconds towards the next whole second in user mode, so it's bounded by 1 million. RUSTime.tvSec is the number of whole seconds the PHP-FPM worker process has spent in kernel mode, so that's system calls, memory mapping, network stack processing, etc. And the same key with USEC instead of sec is the number of microseconds towards the next whole second in kernel mode. The most intuitive mathematical approach to calculating the CPU time duration of the script is to combine the seconds with microseconds and sum the user time and kernel time, and then subtract the start time from the end time, just like we do for the wall clock duration. I was worried that floating point accuracy might be a problem here. Floating point accuracy is 15 to 17 significant figures, so adding everything up to a large total before the final subtraction could cause some precision to be lost. And since the difference between the start and end times will generally be tiny, that loss of resolution could mean we get a result of 0 once the PHP-FPM worker passes a certain age. So maybe it would be better to have a mathematically equivalent but less intuitive formula that subtracts large numbers from large numbers and sums the results at the end. But I tried some rough calculations, and actually the loss of resolution happens sometime after 250 years. So yes, the intuitive formula will do fine. The CPU time duration will inform our decision on setting the PHP directive max execution, and the wall clock duration helps with the PHP-FPM directive request terminate timeout. The last two methods are to log the size of the response headers and the body. The only thing to note here is that the headers are ASCII only, so we can always safely use strlen, which is faster than the multibyte equivalent MB_strlen. The body is UTF-8, so potentially non-ASCII, so we can only use strlen as long as in php.ini we set mbstring.funcoverload to 0. Otherwise, we'd have to use mb_strlen and specify 8-bit encoding to be sure we're getting the number of bytes instead of the number of characters. Then we add a listener for the database to add the query time to the query duration array we just created. And next, we configure the rate limiter, although it isn't actually applied at this point in the request. Nginx rate limits by IP and intercepts those requests before they reach Laravel. So in Laravel, we're limiting by user ID, and that needs to happen after authentication. For us, it happens later in routes/api.php, straight after the authentication middleware. Malicious users can get around this with a coordinated system of multiple accounts and multiple IPs. If we were worried about that, and we couldn't control user accounts or whitelisted IPs more tightly, then we might consider running pattern recognition of usage, i.e., combine the usage of 2 or more users, assess them as if they were a single user, and see if it adds up to a malicious usage pattern. Or we might try to gather a list of known VPN IP addresses and monitor those accounts more closely. For Nginx's rate limit on IP addresses, we need to consider if our clients are in a business at the same address. For example, if all users log on at 9 AM on the same IP address, then we might need to loosen Nginx's rate limit on IP addresses. Next, the request hits the middleware. I've disabled global middleware and moved most of the default middleware to the API group. That's because the web group can only be accessed internally within the Kubernetes cluster. For trust proxies, we're providing the CIDR range that the Ingress controller is guaranteed to be within. And then Laravel knows that the client's IP is the real IP and that the connection is indeed secure. Then API requests pass to root/api.php. And for routes that require authentication, the requests pass through the authentication middleware and the rate limiter middleware we discussed earlier. I extended the authenticate class as a convenient way to add the user ID to the context of logs created after authentication. And also because in the original class, if an unauthenticated request didn't have the accept header of application/JSON, it tried to redirect the user to a login page, but our API is purely JSON, so that's not the desired behavior. The last endpoint is for browsers to report content security policy violations, which go straight into the log. The web routes are mostly for the Kubernetes probes mentioned earlier. /Laravel readiness simply replies immediately. /Laravel startup, if you recall, tests the connections to the database and the cache in a try-catch block and returns an error HTTP status code if there's any problem. And /Laravel status is for my own tinkering and analysis of real cache and op cache in production to further tweak those configurations. Unfortunately, we can't just run those commands in the command line interface because the CLI is separate from PHP-FPM and maintains its own op cache memory pool. And finally, an API request runs back through the middleware. The handle cause middleware along with its config, lets us tell browsers that the Vue.js frontend is permitted to access the API, and the inject meta middleware adds the meta object to each JSON response object as it's passing out of the door. After the response has been sent, the last action is to log the request for future analysis. I won't cover the Vue.js frontend because this video is already quite long, and it just logs into the API, stores the token, and interacts with the API in a simple manner. All the source code is available in the description of the video, and please let me know if you have any questions or any improvements on any part of the code. Thanks.